Once upon a time, in the 17th century, a self-proclaimed chevalier was walking the streets of France, and as bold as a Frenchman in the 17th century could be, he decided to use his wit to make a quick buck, ripping other people off. So, he walked to the downtown pub and announced his entrance most flagrantly.
Good evening, fine gentlemen. Will anyone care for some entertainment to lighten up your drinks?
Boos and screams echoed across the tavern.
Soft clown.
The world's a stage, and the stage a world for entertainment, gentlemen. I insist.
Afterwards, a couple of fellows reluctantly invited him to their table.
Hey clown, come here.
I bring you the gift of a game, of a chance each fine evening. For you, 2 gold coins says I can roll a pair of sixes in 24 rolls or less. Do we have a deal?
Hey, I can do.
Bravo! For you, 2 gold coins says I can roll a 6 in 4 rolls or less. Sounds good.
No deal. I want his bet as well.
Oh, but why? The odds are the same.
You try to rip me off, you ill-willed buffoon.
Ah! Now we're going to talk about of how this game works in a mathematician way, so we can take a closer look. First, we'll start with getting the probability of a 6 in a 4 rolls with 1 dice. First, we get the probability of getting a 6, that is 1/6, and the probability of not getting a 6, that is 5 sixes. Now, let's go to the game. In the first roll, we have the probability of getting a 6. As we saw, that is 1/6. And the probability of not getting a 6, that is 5 sixes. Now, let's go to the second roll, where we have different cases, 3 cases in total. First, we have the probability that we won in that we didn't won in the first game. Then we have the second case that is we didn't won in the second case, and the third case it will be that we won in the second roll. As we can see, we have the probabilities with this that we didn't won and we won, and they sum up to a total of 1. And we can see we can do this process until the 4th roll, and we can see that in the 4th roll we have 5 different cases. The first case is that we didn't won in the first roll, but we won in the second one. We didn't won in the second roll, but we won in the third. We didn't won in the third roll, but we won in the fourth, or we lose in the 4th roll. So we can see the Chevalier de Meré has 52% win rate to win and 48% to lose. So we can see that it's a better probability for the Chevalier de Meré to win this game with a 52%. That is higher than the losing.
Well, now we're gonna explain the probability of getting 2 sixes in 24 rolls of 2 dice. As we know, getting 2 sixes with 2 dice sums 12, and it's the only way to getting a 12. That's why we consider the probability of x equal 12, which we know is 1/6 of the first dice times 1/6 the other dice, which is this 0.02, and the complement of this probability, that is the probability that x is different from 12, is 0.97. And after this, we're gonna explain the 24 cases in which we have a similar process than in the first case, which means in the first roll, we have the original probabilities of winning and losing or rolling again. In this case, we can see that after this first try, if in the case we need to roll again, then we proceed to this second try, second roll, which is the probability of losing in the first try and the probability of getting the 12. This is similar in all the cases here. The only difference is that we are considering that in each scenario we have to add the previous tries. It means if you are in the third try, you necessarily have to lose or to roll again 2 times before, and this is why probability gets modified in each try. In the case of rolling again, it's just the probability of don't getting a 6 once, then twice, and so on until the 24 cases. We have to get 2 6s in 24 rolls. And here, as we can observe, considering the last scenario, in the 24th try, we see that we have 25 previous cases in which to arrive to this one, you should have lost the 23 times before. Then, after this, if we sum the probability of winning, it's important to consider that to win, we have to only get one of these, is 49%, and the probability of rolling again is 51%. This means that probability of losing is bigger than the probability of winning, and if only it's 2%, it's also losing probability. And it's important to note here that both probabilities sum up to 1, that we consider 2 cases, losing or winning, within a process of 24 scenarios or cases.
It's funny to see how often probability defies intuition, because one would think that since the probability of getting a 6 in a single roll with 1 die is 6 times more likely than getting 2 6s with 2 dice, then the median number of times that you would need to roll to get the 2 6s would be 6 times higher than with just 1 die, 1 6. And if we only consider 1 roll, this is the case. We can see that since the probability here is 1 6 times 1 6, then it's 6 times less likely than this probability here, which is just 1 6. However, our little experiment says that the probability of getting a 6 in 4 rolls with 1 die is higher than the probability of getting 2 6s in 24 rolls with 2 dice, 52% against 49%. So why does this happen? Well, as we saw in 2 experiments above, when we consider consecutive rolls, the number of scenarios is the number of rolls plus 1. Because, for example, in this case, we've got 24 possible winning rolls and 1 possible losing roll. So 24 plus 1, 25. One more roll in the second scenario would take the probability of winning above 50%. This means if we consider 25 rolls, for example, our experiment would yield a probability of up 50%. So if we divide 25 by 6, which would be the adjustment for the 6 times less likely thingy, we get 4 and 1/6. This means that the median in the second scenario is higher than the one in the first scenario, even after we account for the additional die. So in conclusion, mathematics defies our intuition. Since the medians are not the same when adjusting for the second die or proportional, so to speak, because 4 times 6 is 24, but we observe that the median in the second case is actually 25.